In our last module, we have seen sequence, series, their convergences. We have also discussed different tests for convergence of ordinary series and sequence. And in our just previous module, we have defined a new type of functions known as sequence of functions. Actually, a sequence of functions is nothing but some sequences involving one extra variable x. So, it is natural that convergence of such sequences will also depend on x, and depending on the nature of x for convergence, we get either pointwise convergence or uniform convergence. In this module, we shall discuss pointwise convergence of sequence of functions. We shall also give some examples on pointwise convergence, and also give the method to decide the limit function for pointwise convergence, and also discuss some consequences of pointwise convergence. So, we have just discussed convergence of sequences. Now, we shall discuss in this module another concept which is known as convergence of series and their applications in probability theory and large sample theory. So, in our last module, we have discussed just defined sequence of functions, and we have seen that for fixed x, a sequence of function becomes a ordinary sequence. In this module, we shall discuss a convergence of such sequence of functions in details. Actually, a sequence of function depends on n and x. Therefore, the convergence depends on x. So, depending on the involvement of x, we have either pointwise convergence or uniform convergence. So, in this module, we start with pointwise convergence, define pointwise convergence, and give some example to discuss the utility of pointwise convergence. So, formally, suppose f(n)x is a sequence of functions on A to R. That is, as usual, f(n)x is a function from A to real line. Then f(n)x is said to converge pointwise on A if for every x belonging to A, the sequence converges. Thus, for every fixed x0 belonging to A, the sequence f(n)x0 converges, and hence there exists some fx0 such that limit of fn(x0) equals fx0. Since x0 is fixed, fx exists for every x belonging to A. Such f is defined as the limit function or the pointwise limit function of fn(x), and we write fn converging to f with the mode of convergence as pointwise. So, the first problem is to decide a limit function f. Although we have seen that there is some fn of which the limit is denoted by f, but how to find f in actual practice? Actually, in practice, getting such an f is not an easy task. So, we shall explain deciding an f using some examples. Consider the sequence of functions x square by n, where x belonging to the closed interval 0, 1. Naturally, this is a sequence of functions involving n and x both. Let us plot the function for different values of n on the same graph paper. In addition, we also consider the function x to the power n, that is sequence of functions x to the power n for x belonging to 0 to 1 for different values of n. The plot is given in the next slide. So, in the leftmost picture, we have plotted x square divided by n, and in the rightmost panel, we have the graph of x to the power n. Now, we find that as we plot x square by n for different values of n, we get either f1, the curve of f1, or f2 or f3, and so on. So, this from the graph it can be seen that f1 is over all the graphs, then comes f2, and then comes f3, and the curves gradually decreases to the 0 line. So this indicates that our limit function might be say f(x) equal to 0 for x belonging to 0 to 1. Next, consider our next example, which is the graph of x to the power n. Now for n equal to 1, we get a straight line which is indicated by f1, and for n equal to 2, we get x square, which is something like a parabola, and we have indicated this in the graph by f2, and then get f3, f4 and so on. So as we increase n, we get that the functions actually become close to the 0 mark. So this indicates that for large n, we might have 0 as a limit function. So this suggests to take f(x) equal to 0 over x belonging to 0, 1 for the purpose. So formally, for the first figure, the functions approach 0 as we increase n. Then it is easy to take the limit function, or easy to define the limit function f(x) equal to 0 for x belonging to 0, 1, and intuitively the above can be justified as for fixed x square by n tends to 0 as n tends to infinity. However, for the second function, we get a sequence of decreasing curves. It is easy to expect the horizontal axis as a limit, and this suggests to take the limit function again as f(x) equal to 0 for x belonging to 0, 1. So let us define pointwise limit in a formal way. So from our last discussion, we find that after a large n, the graph becomes very close to the limit function. Obviously, such an n depends on the value of x. Thus, if n converges to f implies that for every x belonging to a and for every positive epsilon, there exists a positive integer nu which is a function of x and epsilon both, such that the distance between fnx and fx, that is absolute value of fnx minus fx, is less than epsilon, is satisfied for every n exceeding nu x epsilon. However, looking at the nature of limit function for fixed x, f is defined in practice. So let us consider some examples. So in our first example, we consider the already plotted function, that is x square by n for x belonging to the real line. Then for fixed x, we find that this fnx converges to 0 as n tends to infinity, and this suggests to take the limit function as 0 for every x belonging to real line. However, this is just a claim that our limit function would be equal to 0 for every x, but we need to justify this choice of the limit function in terms of some nu x epsilon, some feasible choice of nu x epsilon and epsilon. So our claim will be justified if we can find a feasible nu x epsilon as defined above. Now consider the inequality, that is absolute value of fnx minus fx less than epsilon. So while taking this absolute value, we get the function absolute value of x square by n, absolute value of x square by n, and then since x square is a positive quantity, absolute value of x square by n less than epsilon implies n exceeding, or say n greater than equal to box of x square by epsilon plus 1. So the problem here is that n is an integer and x square by epsilon may be some real number. So that's why we have taken the box function, that is the greatest integer contained in x square by epsilon, and since there is a possibility that x square by epsilon may be between 0 to 1, so in that case the box function becomes 0. So we added some quantity 1 for a proper definition. So we get that the absolute value of fnx minus fx is less than epsilon whenever n greater than equal to box of x square by epsilon plus 1. So we get a choice nu x epsilon as box x square by epsilon plus 1. Hence we are quite satisfied that fnx converges to fx pointwise, where fx is defined as 0 for every x belonging to real line. Let us consider our second example. We have already discussed this function through some plots. So our function is, sequence of functions is fn x equal to x to the power n for x belonging to open interval 0, 1. Then for fixed x, we find that x to the power n is a positive fraction, and hence this suggests to take the limit function as 0 and for every x belonging to open interval 0, 1. Now for epsilon greater than equal to 1, absolute value of fn x minus fx, which becomes x to the power n, is less than epsilon, is satisfied for any n greater than equal to 1, because in such a case x to the power n becomes a positive fraction and epsilon is chosen exceeding unity. Therefore, this inequality is satisfied for every natural number n. However, for epsilon belonging to open interval 0, 1, from the inequality that absolute value of fn x minus fx less than epsilon, which means x to the power n less than epsilon, this gives n greater than equal to box of log epsilon divided by log x plus 1. As earlier, one can find the reasoning behind using the box function. Thus, in any case, we can take mu x epsilon as box of log epsilon by log x plus 1. Hence, our claim that fx equal to 0 as a limit function is justifiable, and hence fn x converges to already defined fx pointwise. Consider our next example, which contains the sequence of functions x to the power n divided by n square for x belonging to the open interval -1 to 1. Again, we have already seen that for fixed x, x to the power n tends to 0 and 1 by n square also tends to 0 as n tends to infinity, and this suggests to take our limit function as fx equal to 0 for every x belonging to the open interval -1 plus 1. However, finding a feasible choice or some choice mu x epsilon from the inequality absolute value of fn x minus fx less than epsilon is quite complicated, because this fn x contains some powers of x and divided by n square, and we have to express this inequality in terms of just keeping n in the left hand side and then to just write or to keep the other quantities in the right hand side. So we shall use some trick. We observe that absolute value of x to the power n by n square minus 0 is less than absolute value of 1 by n square minus 0 for every x belonging to open interval -1 plus 1. Thus, absolute value of 1 by n square minus 0 less than epsilon implies absolute value of x to the power n by n square minus 0 is less than epsilon. Now, for epsilon greater than equal to 1, the inequality absolute value of 1 by n square minus 0 less than epsilon is automatically satisfied for every integer n, as 1 by n square is a fraction. However, for epsilon belonging to 0, 1, we get after some little bit mathematics or algebraic manipulation that n greater than equal to box of 1 by square root of epsilon plus 1. Thus, in any case, we can take our mu x epsilon as box of 1 by square root of epsilon plus 1. Therefore, our limit function 0 for x belonging to -1 to +1 is justified by a feasible choice of mu x epsilon, and hence the limit of fn x is fx with mode of convergence pointwise. Consider our next example. This example is not very easy, it's just easy looking, but the convergence, deciding the convergence is not an easy one. So our next sequence of function involves the function nx divided by x plus n for positive x. Then it is quite clear that for fixed x we find n divided by x plus n tends to 1, so that the limit function actually we find that so that our limit function becomes x, and we claim fx equal to x for all x greater than equal to 0 as our limit function. So our claim should be justified in terms of finding a feasible choice of mu x epsilon, and we start from the inequality that absolute value of fn x minus fx, and now we find that this absolute value of fnx minus fx comes out as x square divided by x plus n, and this thing is less than x square by n. Thus, absolute value of fnx minus fx less than epsilon will be satisfied if we choose n in such a way that x square by n less than epsilon is satisfied. Now, x square by n less than epsilon gives n greater than equal to a box of epsilon by x square plus 1. Thus, we can define our new x epsilon as box of epsilon by x square plus 1, which is a feasible choice, and hence limit of fnx equal to x for x greater than equal to 0 pointwise. Consider our next example, which involves a sequence of functions defined by nx divided by x square plus n square for positive x. Then for fixed x, we find that n divided by x square plus n square tends to 0, and hence we take our limit function, or just suspect our limit function as 0 for x greater than equal to 0. Now, the absolute value of fnx minus fx is just nx divided by x square plus n square, which is again less than x by n. Thus, the absolute value of fnx minus fx is less than epsilon is satisfied if x by n is less than epsilon. Now, from the inequality x by n less than epsilon, we get n greater than equal to box of epsilon divided by x plus 1. Thus, if we define mu x epsilon as box of epsilon divided by x plus 1, we get a feasible choice of mu x epsilon, and hence we can justify our limit function, that is fx equal to 0 for all x greater than equal to 0 as a pointwise limit of the sequence of functions. Consider our next example. Consider fnx as nx multiplied by e to the power minus nx for positive x. However, deciding an appropriate limit function is not an easy task, because the limit of nx multiplied by e to the power minus nx as n tends to infinity is not straightforward. Thus, we plot the function for different values of n on the same graph paper to get an idea about the limiting behavior of the sequence of functions. The plot can be found in next page. So, we can see the plot. We find that the function is for every n, the function initially increases to a point and then decreases and touches the x equal to 0 line. So, and as we increase n, we find that the curve becomes almost identical with the x equal to 0 line. So, this suggests to take, or just as a suspect, we can assume that the limit here is 0 for every x greater than equal to 0. So, formally the curve attains a peak and then diminishes to 0 for every n, and as we increase n, the point at which peak is attained becomes nearer to 0. This suggests to take the limit function as fx equal to 0 for x exceeding 0. However, finding a feasible choice of nu x epsilon from the relation absolute value of fnx minus 0 less than epsilon is not an easy task. However, we can use some inequality which is very readily known for exponential functions. Actually, if we expand e to the power nx, we find that the expansion is 1 plus nx whole square by 2 up to infinite number of terms, and since x is assumed to be positive and n is a positive integer, we find the inequality e to the power nx greater than nx by 2, e to the power nx greater than nx square by 2. Thus, absolute value of fnx minus 0 less than epsilon will be satisfied if we can find a nu x epsilon satisfying 2 divided by nx less than epsilon. Now, the latter inequality gives nu x epsilon as box of 2 by x epsilon plus 1, and since we get a feasible choice, limit of fnx equal to 0 for x greater than equal to 0 with mode pointwise. Consider our next example. Suppose fnx is defined as an indicator function where the indicator function takes the value 1 if box x modulus of x less than equal to n, and 0 otherwise. As earlier, the first task is to decide a limit function. Intuitively, it is clear that as we increase n, the more of the real line will be covered and we get the value unity there. Thus, we claim fx equal to 1 for every x. Now, the absolute value of fnx minus fx is nothing but the indicator of absolute value of x greater than n. Clearly, for epsilon greater than equal to 1, absolute value of fnx minus fx is less than epsilon is satisfied for every integer n. However, for epsilon belonging to 0, 1, the above inequality is satisfied whenever absolute value of x less than equal to n, or equivalently n exceeding box of absolute value of x plus 1. So, if we take our nu x epsilon as box of absolute value of x plus 1, we get a feasible choice, and therefore, fnx converges to our claimed fx for every x pointwise. So, we have seen pointwise convergence in the context of sequence of functions. We have also seen some examples on how pointwise convergence works. We have also seen how to decide the limit function for pointwise convergence. However, there is another mode of convergence which is also known as uniform convergence, and in our next module we shall discuss uniform convergence and the criteria, the definition in details, and also support all these things with a number of examples.